Okay, I'm here in my office and I'm going to make a relatively short video for Friday's lecture about some of the content that we started and that we can continue to work on for the next couple of days for homework number 7. I'm going to start off where we kind of ended the lectures today. So we'll start off by just mentioning that this is all about the Laplace transform. And you recall we were doing the example of a dot plus ax equals b, and we had gone through a couple of the different lines in table 2.2, 2.22 and 2.21, I believe, that talked a little bit about how we convert these ordinary differential equations into algebraic expressions. So if you recall, we talked about how we take the Laplace transform of this particular function right here, and taking it of the first x dot, we had s xs minus x0. And of course, this means that the initial conditions for when time equals 0 for this x value. So in general, you'll be receiving a point at which this equation, or rather x, will be satisfied or defined at time equals 0. Let's assume that it is 0, at least initially. We'll continue on with the Laplace transform of the second term. And then on the right-hand side, we'll put b over s, and this makes an assumption that b is constant. And as a result, we can look up one of the lines in table 2.2 to make that sort of connection right there. All right, well, in class on Wednesday, if you're looking at this on Friday, we would factor out this sort of idea right here from xs. We brought this one over, b over s minus x0. And at some point, of course, we can cross off that x0 to be 0 at any moment in time, but for right now, we'll try to keep it up. All right, well, if you recall, we need to isolate xs, so that then we can do the inverse Laplace transform of everything on the right-hand side and on the left, and at the end of the day, we'll be left with the profile of x over all time, or a function of xt. So this one becomes this divided by s plus a, and we can simplify this a little bit by multiplying the top and the bottom by s. And now, as we just barely mentioned at the end of the lecture on Wednesday, we need to convert this into different terms that we can use the table 2.21 and 2.22 to inverse this particular term to get the actual profile of x for all time, or a function of x, the solution to this ordinary differential equation. Well, we do that by recognizing that there are going to be two possible terms. One where the denominator, okay, is one of the factors in this denominator, s, and the other one, which is s plus a. And the reason why we're doing this is because this term right here and this term right here might be very similar to one of the terms inside of the table, and therefore we'll be able to take the inverse Laplace transform for each one of these to extract out again xt for all time. We don't know what those are, and so we're going to put in c1 and c2 to be coefficients for either one of these. And now we need to perform partial fractional expansion. To this equation right here, so that we can extract out c1 and c2. All right, well, I'm going to write it up here at the top, and then we'll be able to kind of follow a little process to extract out c1 and c2 by way of review. Well, there's a couple of things that we can do to kind of isolate C1. The first thing is that if we multiply every single one of the terms in this equation by S, we'll have C1 by itself. Let's do that first. And then we can calculate this particular equation at a particular value of S. If we choose the value of S, which would make the denominator here 0, which means S is equal to 0, okay, and these terms, S equal to 0, we'll be able to hopefully find a way to isolate C1 and extract out the value for the C1 over S term. Well, the way we do that, of course, is that we can cross off these two S's. They're going to cancel each other out, and then replace all the S's with 0. So this will become B over A, once these two S's become 0. And over here, 0 from this guy right here times C2 over S plus A, or 0 plus A, which is over A, is going to also be equal to 0. Which means then we're left that C1 is equal to B over A. Let's do now the same sort of thing with C2. For this particular equation then, I've taken the top one and multiplied all the terms by S plus A, and I've gone ahead and already canceled out the S plus A over the S plus A. And then we can also replace all the S's with minus A at a particular value to see then what sort of term we'll get for C2, which will satisfy this equation. Again, we can cross these guys off right here. This one will become 0 through S equals minus A, through this term right here. And then we'll be left with, well, B minus A x0 all over minus A. We replace this S with a negative A. So now that we've got both C1 and C2, we can come over here and we can express this particular ratio as the sum of two terms, C1, which is B over A, plus this whole term right here, which is B over negative A minus x0 all over S plus A. We can do a little bit of rearranging, okay, in the sense that this A got canceled with this one to give that negative sign, and this one canceled with that one, but we can bring it up here. Okay, so now I've written it as three different terms, but of course, if we start to put in the initial condition for x0 is equal to 0, this whole term goes away. I'll leave it there so we can kind of see what happens to the equation when we solve it. All right. Now we need to take the inverse Laplace transform of all three of these terms, which means then that xt is going to equal the inverse Laplace transform of xs, which is then going to be the inverse Laplace transform of these three terms right here. B over A over S minus B over A over S plus A, and then plus minus x0 over S plus A. All right, we've now put these three terms, or these terms, in a position where we can look up the inverse Laplace transform. And if you recall from class on Wednesday, we know this is going to be B over A, a constant term. This value right here is going to be B over A times E minus AT. And similarly, this one right here will be E x0 times e to the minus at. If we set x0 to be 0, well, we're left with the result that we've seen in the other two methods. Of this guy right here. Now, let's talk a little bit about this particular function right here. Now, first of all, we know that if time approaches infinity, well, this xt is going to reach some sort of static equilibrium state. We call it the steady state value. So if x approaches infinity, well, then xt will approach b over a. So we would call this term the steady state term. Which means then that anything that's not the steady state term is going to be the transient response. Effectively, in the solution to these equations of motion, you can break up any equation into one or the other. Either the steady state part, the stuff that's going to remain when time is equal to infinity, or the transient part, the transient response, the stuff that is temporary and will eventually decay over time potentially. All right, let's do another problem. And we'll talk a little bit more about the different responses in different parts of these different equations. All right, the next example that we're going to do is question 214c, and it's something quite similar. We have 5 times x dot plus 7x equals 15. In this case, we're defining something for the a and something for the b. And it becomes very similar in the sense that we need to take this and do the Laplace transform of it. So we can do 5 times s xs minus x0, okay? Which means that we need to go off and take a look at the problem. The problem is that the initial condition is set to be 4, but I'll leave it like x0 for the time being. And then we need to add 7 times xs, just like we did in the previous example, and that's going to be equal to 15 over s. Since we know that the Laplace transform of any constant value, according to table 2.22 and 2.21, is going to be 15 over s. Well, we do the same sort of thing. We're going to gather up all the terms. So we're going to have 5s plus 7 times xs. There's going to be something right here of minus 5 times x0 equals 15 over s. Well, we still need to isolate this xs. So let's do it right now. We have 15s plus 5x0 all over 5s plus 7. And so similar to before, now we need to kind of see what can we do to make this particular term into a set of other terms that we can find in table 2.2 and 2.1, so on and so forth, that we can inverse Laplace transform it to extract out and identify xt. Well, first of all, we'll multiply the top and the bottom by s. So I'll do s 5 x0 over s 5 s plus 7. And to make it even easier, I'll also divide the top and the bottom by 5. 3 plus s x0 over s plus 7/5. Okay, and so make sure that you see that that is actually an s. All right, well, now we need to go off and do some partial fraction expansion. So we'll write it up here again as 3 plus s x0 And we need the same sort of thing like we did before, where we need to identify, well, what C1 is and what is C2. So we'll multiply both sides by S. We'll set S to be 0, the value at which this denominator would be equal to 0. These cross off, and we're going to be left with this equals C1. Why do I not need to include C2? Well, because once I multiply this term by S, and then I make S equal 0, this whole term will be canceled out. So now I'm left with this idea where 3 over 7/5 is equal to C1. And to make it more obvious, I'll just say that that is equal to 15 over 7. Once I multiply the top and the bottom by 5. Okay, let's do the same thing for C2. This is all going to be when S equals minus 7/5. The value of S that would make this denominator equal to 0. That's going to be equal to C2. These two terms are going to be canceled off. And so I'm left with 3 plus minus 7/5 x0 all over minus 7/5. All right, well, it's a bit of a mess right here, so I'm going to multiply the top and the bottom by 5. And then I'm actually going to divide it up so that it's equal to 15 over 7 minus plus x0. At any time, I can actually put x0 to be equal to 4 right here. Well, if that's the case, let's now use this equation. And in this case, I'm going to just come in here and replace C2 with this value. So minus 15 over 7 plus x0. I'm going to replace C1 with 15 over 7. And now I can invert, or rather apply the inverse Laplace transform to each one of these terms, although I will take a second to make it into 3 different terms. Now I'm going to take each one of these and I'm going to invert through the inverse Laplace transform these. I'm left with 15 over 7 minus 15 over 7 times e to the minus 7/5 t, and then plus x0 times e to the minus 7/5 t. So this is the solution, and there's a couple of things that we should probably look at. First of all, we can identify the steady state value. So we can find the steady state value by changing t to infinity. That's of course the steady state value of x. So if this goes to infinity and this goes to infinity, we know that this term right here is SS for steady state. Which means then that the other two terms are going to be the transient response. So there's 2 other ways that you can classify these various terms inside the solution of xt. The first thing you should notice is that 2 of these terms have 15 right here. If you recall from the lecture on Wednesday, this right here is an external force. Which means then that external forces would result in some sort of forced response. So these 2 terms are called the forced response of the system. And everything else which isn't forced is going to be the free response. The free response is calculated when you remove all the external forces. So if you set this to be 0, which means this becomes 0, this is 0, 0, so on and so forth, both of these become 0, you're left with the free response. It's what happens to this particular system when you don't have any external forces and you just leave it to the initial conditions to drive. So as a result then, you can get the full response is equal to forced plus free. And likewise, the full response is equal to the steady state response plus the transient response. Each one of these will help you identify if you've got the solution correct or not. Furthermore, every single term inside your solution has to be classified as either forced or free and either as steady state or transient, which means that there's 4 combinations for every single term. It can be forced and steady state, forced and transient. It can be free and steady state, or it can be free and transient. Let's do one more problem, and then we'll try to talk a little bit about these and identify which is which. Okay, so for this last example, I'm going to do example 215b from the textbook, and it's got a second order derivative. You'll notice then that the external forces are 0, so we expect this to be something similar to a free response. I now need 2 initial conditions because I need to satisfy the initial conditions for a second order system, but it becomes the same process where now I need to take that Laplace transform of this equation and then eventually invert that Laplace transform once I've got various partial fractions that have expanded from my initial Laplace transform process. This whole set of 3 terms is nothing more than the inverse, or rather the Laplace transform of x double dot. This set of 2 terms with the 14 in front of it is the Laplace transform of the second term. And of course, this last one is nothing more than 49 times, well, the Laplace transform of x. Right-hand side will also be 0, or 0 over s, which is also equivalent to 0. All right, well, now I'm going to collect all the terms for xs. So s squared is right here. There's 14s right here. And then there's a 49 at the end, all times xs, when I factor out the xs. You should notice that this is interestingly very similar to this particular set of coefficients right here. I'm going to bring everything over the other side. So I'm going to have a positive s x0 from this term right here, a positive x0 dot from right here, okay? And then this term right here is going to be a plus 14 x0 minus conditions. Well, that's going to mean that I have xs, which is equal to this whole term right here, s times x0 plus, I'm going to bring that over, 14x0, okay, plus x dot 0, all over this term in front of the xs, s squared plus 14s plus 49. Okay, so this is a complicated ratio, and it doesn't exist anywhere in our table, although there might be things that we can do to change it into some sort of set of fractions that would allow us then to take this and convert it back into xt so that we can solve this system of equations, or in this case, second order ordinary differential equation. Well, we should recognize that this denominator value, which we're going to start calling the characteristic equation, okay, has a way to simplify it, because we can see that it's actually a squared value of s plus 7 squared. And we'll carry over everything else on the top. sx0 plus 14x0 plus x dot 0. So all that factoring and polynomials that you did in previous years will start to come to play when we start to mess with these denominator terms, or rather the characteristic polynomial. Well, this s plus 7 squared is getting a little bit closer to some of the terms that we've seen in tables 2.21 and 2.22. And so what we can do is the same sort of thing where we can start to break it out and see if we can establish some simpler terms that then can be inverted through the inverse Laplace transform. Well, the first thing I'm going to do is take a look at this term right here. Okay, so we have s plus 14x times x0. That's just factoring out the x0 plus x dot 0 all over s plus 7 squared. Okay, and it can be equal to, well, maybe, potentially, two terms, one of which is s plus 7, and the other one which is s plus 7 squared. Whoops, I made a little mistake right here. This is just s plus 14. Well, let's see, first of all, if our classic way of partial fraction expansion will work. So I'll multiply the top and the bottom. And you can see here that one of the denominator terms will cancel with that one that I put on the top half. But when I replace s with minus 7, I'm still going to have an undefined denominator, because a 0 in the denominator is undefined. So I can't do the classic sort of thing that I've done before. What about the other option? What if I multiplied both sides by s plus 7 squared? Well, if I'm multiplying s by 7 squared, this becomes c2, and I can square this term, and then I can finally cancel off both of these guys right here. Why can I do that? Well, because when I multiply this by s plus 7 squared on the top and the bottom, on the top, I can cancel one of those off, and then when I replace this term right here with s equals minus 7, this whole value then becomes 0, and I'm left with then, I can at least find the coefficient in front of this term, but not the other one. So I can replace these s's with minus 7, so I'm going to do so. Minus 7 plus 14 times x0 plus x0 dot all over, well, 1. So C2 equals 7 x0 plus x dot 0. And if I want to, I can replace this x dot 0 with 3 and this x0 with 1. All right, well, if C2 is this value right here, well, I might be able to figure out a way then to get C1 if I replace C2 and look at the comparison terms. So I'm going to erase this term right here. I'm going to replace C2 with this equality. And now I need to ask myself, well, what position or value of C1 will satisfy the top and the bottom? Well, if I multiply the top by s plus 7, I have to do it to the bottom right here. Then I can cross off all the denominators. And now I can look for small little equations that will be equal to each other. For example, on the right-hand side, I've got C1 times S. That's going to have to equal S plus X0. Well, this little equation is easy to solve for C1. X0 is nothing but C1 right here. So now I can go back and I can rewrite my equations. Is going to equal x0 over s plus 7 plus 7x0 plus x dot 0 all over s plus 7 squared. Now I need to go off and see what the values are for these two terms and if they exist inside table 2.21 and table 2.22. Well, x0 times e to the minus 7t will be the inverse Laplace transform of this term right here. And then I can break this up into two other terms. I'll make it be 7x0. This time it's squared, so there's a different line inside of table 2.21. In this case, it's t times e to the minus 7t for this guy. And this last term right here is going to be plus x0 dot t times e to the minus 7t. I'm going to write this equation up here. All right. Well, the first thing we should recognize is that because the input to this system is 0, we expect everything to be, well, the free response. Which means then this term, let's just call it 0, is the forced response. There is no forced response in this particular equation. Well, what about steady state? Well, we take a look at t goes to infinity. So all of these values right here will be the transient response. And as t approaches infinity, well, this goes to 0, but these two terms would go to infinity, so there's no steady state. Or another way of looking at it is that this little term right here is steady state. But effectively, since this is a term that really doesn't matter, there's no forced response and there's no steady state in this particular equation. But the rules are still satisfied that every term must be either free or forced, and every term must be either transient or steady state. It's going to have two classifiers in each one of them. I can replace all these values. X0 becomes 1 plus 7 1t e to the minus 7t, and then x0 dot is 3 t e to the minus 7t, and then finally a solution for this particular set of initial conditions will be e to the minus 7t plus 10t e to the minus 7t, and that is the solution for this second order ordinary differential equation. So, with the skills and the discussion of free and forced and transient and steady, you'll be able to answer a majority of the questions. But on Monday, we will discuss the initial value theorem, the final value theorem, and transfer functions on Monday. Have a great weekend, and we'll see you next week.